Alright, section 1.7 talks about the precise definition of a limit. Here's the definition. I'm going to give you an example to go with that so that, we kind of grasp what they're talking about. From theoretical point of view, this makes total sense. Since you're not very comfortable with that, it's going to be a bit hard to grasp. So let's go over that. Precise definition of a limit. Let f be a function defined on open interval containing this value a, except possibly at a itself. Then we say that the limit as x approaches a of f of x equal L if for every epsilon bigger than 0. What's epsilon? A very small number. I'll show you in an example. There exists another small number such that whenever you choose this difference, which is the difference between those to be that small, you'll get the difference between those two to be that small. What the heck does that mean? The limit as x approaches 1 of x squared minus 1 over x minus 1. I know that is, now that I know a lot about limits, throw the 1 in, I know that's a 2. But if I didn't know it was a 2, this is what this says. It says when you do a limit, don't you pick values? Oh, you know what? I'm going to switch those so that I could use that space more if needed. I'm going to pick a value of x and figure out what x squared minus 1 over x minus 1 is. I know we did that already, and I have all of these points. When I say, and this is the catch, this is what they're talking about, this part. When I say give me a value close to 1, if you say 0.9, right? Then they're saying, what is the difference between x, which is the 1, and the 0.9? Isn't that 0.1? Then wouldn't you say 0.99 and then 0.999? So the difference between those is a very small number. This right here is the delta they're talking about. Now what happens? When I plug this in, I'll get 1.9, I'll get 1.99, and I'll get 1.999. Now we're talking about this. If I take the difference between, it's an absolute value, it doesn't matter how you write it. F of x is actually 1.9, that's this part, minus L. L is a 2. Do you see that's 0.1? 1.99 minus 2, that is 0.001. And 1.999 minus 2, that is 0.00. I messed up on one of the zeros here. So do you know what this is saying? This is saying for those numbers to be close enough, if you take the difference between those and this, it should be an extremely small number. Graphically, this is what it's saying. If I'm looking at a graph of y equals some f of x, it says if you take the limit as x approaches a and get an L. When I say pick values close to the 2, or to the 1, which in our case is the a, if you move an delta to the right and a delta to the left, then the values of y should be around this L by no more than an epsilon above and epsilon below. Meaning, when you pick values very close to 1, the y values should be leveling off next to 2. And that's the actual definition. That makes a lot of sense from a theoretical point of view. Alright? So we're going to apply this. I'm going to point this up again in my next example. I'm looking at problem number 14, and this is on page 82. We're going back to chapter 1. Given that the limit as x approaches 5x minus 7 equals 3, we know that since that's a polynomial, plug it in. 10 minus 7 is 3. Perfect. Illustrate the values of delta that correspond. So this is normally what happens. Normally this number is given. When they place an order, when they say we'd like you to make a door, that we want it to be 8 feet, they have to give you a margin of error. They'll say, you know, we'll accept it if it's above 8 feet by this much or below 8 feet by this much. That's this part. Your job is to figure out what to set the machinery on to get it that accurate. Remember, the more accurate, the more expensive it costs. So it makes a big difference whether I'm making a door I'm going to put on my house or a door I'm going to put on a submarine. You know, the more precise the door is, or the more precise the whatever it is I'm making is, the more expensive it is. So let's start with the simple definition. Limit as x approaches 2 of 5x minus 7. We know it equals 3. I'm going to make a chart really quick. So this is what they want. They want first delta, epsilon to be 0.01. And remember what that is. That is the difference between the y's. They want the y's to be accurate to the 10th. Yeah, to the 10th decimal place. So I'm going to start by picking values close to 2. Let's say 2.1. I plug that in my calculator, I'll get 3.5. I'll plug in 2.01. So here, if I took 3 minus 3.5, I'm off by 0.5. That's big. If I put 2.01, I'll get 3.05 from my calculator. If I take the difference between the 3 and the 3.05, do you see that's 0.05? I say, okay, well, I didn't hit a 0 point, but I hit this part. I hit this mark. So for this mark, for this part right here, to have an epsilon of 0.01, I need delta to be what? The difference between those two, 0.01. They're matching. And since these values could be anything, and this is very tedious, somebody came up with an idea. Somebody said, you know what, why use trial and error? Why keep on doing this until you figure out what that is? Why not work out what you can control? What do you control? You're picking values of x. You can control the difference between x and 2. When I say 2.1, 2.1 minus 2 is 0.01. That I can control. Well, let's see how that works. What should I set that equal so that I'll get that epsilon that they got? What they want the absolute value of f of x minus L to be less than this epsilon, right? That's what they want. Well, let's see. What's f of x? F of x is 5x minus 7 minus L. L is the limit. That's a 3. That is 5x minus 10. I have no control over any of those. The only thing I can control is how to choose x. Can't I factor a 5 out of this? And they want all of that to be less than epsilon. Now, I'm getting too excited. Isn't that saying x minus 2 is less than epsilon over 5? But wait a minute. This is this. I have control over that. That's my delta. Right? That's the number I choose. If I let delta equal epsilon over 5, I nailed it. I don't have to do trial and error in all of these cases. And let me show you. So, instead of doing this trial and error, watch how this is going to work. I'm going to restart this problem. But now that I know this, I'm going to say 5x minus 7. I'm going to say, when you want epsilon to be 0.1, let delta equal what? If I take 0.1 divided by 5, that should do the trick. And when I want epsilon to be 0.05, I'm going to take 0.05 divided by 5. And when I want epsilon to be 0.01, I'm going to choose 0.01 divided by 5. I'm going to put that in a calculator and come right back. So this pretty much tells me what to do. It says, look, if you want this accuracy, choose this number. If you want this accuracy, choose this number. And if you want this accuracy, choose this number. Meaning what? Well, how far am I from 2? I'm going to 2. Move away from 2 by that much. If I take 2.05, and for the blue, 2.01, and for the green, 2.002. Okay, there's a typo. This should have been 2.002. I fixed that. And here's my calculator. So if I go by evaluating this, remember how to do that? 5, the answer minus 7, enter. Now, let me go in and put in 2.02. Now it's stored in my answer. Go back. I'll get 3.1. And do you see the accuracy here? By moving away by 0.02, I was able to get away from 3 by a 0.1, meaning if you take 3 minus 3.1 in absolute value, you get 0.1, which is desired. If I want to get this accuracy, all what I have to do now is use this. And if I go in and get my calculator again, take 2.01, I'll get 3.05. What do you know? If you take the difference between 3 and this, you will get 0.05, which is what they want. And if they want it to be this accurate, that's the x value that you choose, and that is 2.002, enter. And there it is, 3.01. What do you know? So instead of using trial and error, somebody figured out if you do this. Now you might be thinking, wait a minute, but how did we know we were going to get x minus 2? Because that's what we have control over. Well, if the limit exists, you will always get an x minus 2. And then you'll know what to do with whatever order they want. So pretty much, we don't go in and invent that door and then measure it to figure out whether, hey, wait, does it satisfy those conditions or not? No. We figure out how accurate we want it to be, and we set the machinery to build it that way, right? We want to make 1 gallon of milk. We don't have machinery pull different, volumes and then measure them after. No, we set the machinery at a certain values, and we know our margin of error from our machinery. The more accuracy of a machinery we have, the more expensive it's going to be. And that's how it works. So somebody figured this out, and that's what we're going to use for the rest of the section. The section doesn't deal with you just doing this. Actually, it deals with you with doing an official proof by using one definition. Just that definition. For every number epsilon bigger than 0, there exists a delta bigger than 0 such that. Now let me elaborate on the notation really quick. So anytime you see for every, we use upside down A. There is backwards E such that backwards epsilon. I'll use the words and those until we get used to it. Now we're going to do some more problems. I'll do that in the next video. Now I'm going to share my calculator with you.